Hey, what's going on, guys? My name is Addr Command. Welcome back to Save Our System IT. Today I'll continue the 10th part of our BusyBox series. This program sets or gets the IO scheduling class in priority for a program. If no arguments or just the -p option is given, ionice will query the current IO scheduling class in priority for that process. A process can be in one of three scheduling classes. The idle class, a program running with idle IO priority, will only get disk time when no other program has asked for disk IO for a defined grace period. The impact of idle IO processes on a normal system activity should be 0. The scheduling class does not take a priority argument, and presently this scheduling class is permitted for an ordinary user since kernel 2.6.25. Then we have the best effort class. This is the effective scheduling class for any process that has not asked for a specific IO priority. This class takes a priority argument from 0 to 7, with the lower number being a higher priority. Programs running at the same best effort priority are served in a round-robin fashion. Note that before kernel 2.6.26, a process that has not asked for an IO priority formally uses none as scheduling class. But the IO scheduler will treat such processes as if it were the best effort class. The priority within the best effort class will be dynamically derived from the CPU nice level of the process. The IO priority will be the CPU nice plus 20 squared by 5. For kernels after 2.6.26 with the CFQ IO scheduler, a process that has not asked for an IO priority inherits a CPU scheduling class. The IO priority is derived from the CPU nice level of the process. And then we have the real-time class. The RT scheduling class is given first access to the disk, regardless of what else is going on in the system. Thus, the RT class needs to be used with some care, as it can start other processes. As with the best effort class, 8 priority levels are defined, denoting how big a time slice a given process will receive on each scheduling window. This scheduling class is not permitted for an ordinary non-root user. The IP command is very versatile, and it's used to show and manipulate routing, devices, policy routing, and tunnels. The names of all objects may be written in full or abbreviated form, meaning address is abbreviated as ADDR or just the letter A. The set of possible actions depends on the object type. As a rule, it is possible to edit or show or list objects. But some objects do not allow all of these operations or have some additional commands. The help command is available for all objects. It prints out a list of available commands and argument syntax conventions. If no command is given, some default command is assumed. Usually it is a list, or if the objects of this class cannot be listed, help. Link is a network device, and the corresponding command displays and changes the state of devices. The address is a protocol, IP or IPv6 address, attached to a network device. Each device must have at least one address to use the corresponding protocol. It is possible to have several different addresses attached to one device. These addresses are not discriminated, so that the term alias is not quite appropriate for them, and we do not use it here. The IP Addr command displays addresses and their properties, adds new addresses and deletes old ones. The arguments for IP address delete are the same as the arguments for IP Addr add. The device name is a required argument, the rest are optional. If no arguments are given, the first address is deleted. Flush commands are pretty dangerous. If you make a mistake, it will not forgive it, but will cruelly purge all addresses. IP address flush, this command flushes the protocol addresses selected by some criteria. The difference is that it does not run when no arguments are given. IP route flush, this command flushes routes selected by some criteria. The arguments have the same syntax and semantics as the arguments of IP routes show, but routing tables are not listed but purged. The only difference is the default action. Show dumps all the IP main routing tables, but flush prints the helper page. IP route get, this command gets a single route to a destination and prints its contents exactly as the kernel sees it. IP rule is for routing policy database management. Rules in the routing policy database control the route selection algorithm. Classic routing algorithms used in the internet make routing decisions based only on the destination address of packets, and in theory but not in practice on the TOS field. In some circumstances, we want to route packets differently depending not only on destination addresses but also on other packet fields. Source address, IP protocol, transfer protocol ports, or even packet payload. This task is called policy routing. To solve this task, the conventional destination-based routing table, ordered according to the longest match rule, is replaced with a routing policy database, or RPDB, which selects routes by executing some set of rules. Each policy routing rule consists of a selector and an action predicate. The RPDB is scanned in order of increasing priority. The selector of each rule is applied to source address, destination address, incoming interface, TOS, and FW mark. And if the selector matches the packet, the action is performed. The action predicate may return a success. In this case, it will either give a route or failure indication, and the RPDB lookup is terminated. Otherwise, the RPDB program continues on the next rule. When doing any moderate to advanced networking, you're likely to have to deal with subnetting. While some people have an ability to do the binary math in their head to figure out the correct subnet mask, some may find it difficult to calculate. For them, ipcalc is a tool in Linux which helps them to calculate the number of subnets, subnetting mask, and other IP addressing related stuff. ipcalc takes an IP address and net mask and calculates the resulting broadcast, network, Cisco wildcard mask, and host range. By giving a second net mask, you can design subnets and supernets. It's also intended to be a teaching tool and presents the subnetting results as easy to understand binary values. Kill is used to send a signal to a process. The default signal for kill is term, which will terminate or kill the process. Use -L or -L to list available signals. Particularly useful signals include HUP, int, kill, stop, count, and 0. Alternate signals may be specified in three ways: -9, -sig-kill, or -kill. Negative PID, or process ID values, may be used to choose whole process groups. See the PGID column in the output of the PS command. A PID of -1 is special. It indicates all processes except two, the kill process itself and init. Killall kills processes by name. Killall sends a signal to all processes running any of the specified commands. If no signal name is specified, sigterm is sent. Signals can be specified either by name, like hup or sighup, or by number, or by the option -s. If the command name is not a regular expression and contains a slash, processes executing that particular file will be selected for killing, independent of their name. Killall returns a 0 return code if at least one process has been killed for each listed command, or no commands are listed and at least one process matched the -u and -Z search criteria, and killall returns non-zero otherwise. A killall process never kills itself but may kill other killall processes. The functionality of the kernel log daemon has been typically incorporated into other versions of system log daemon, but this seems to be a poor place for it. In the modern Linux kernel, a number of kernel messaging issues such as sourcing, prioritizing, and resolution of kernel addresses must be addressed. Incorporating kernel logging to a separate process offers a cleaner separation of services. In Linux, there are two potential sources of kernel log information: the /proc file system and the system call interface, although ultimately they are one and the same. Kernel log daemon is designed to choose whichever source of information is the most appropriate. It does this by first checking for a presence of a mounted /proc file system. If this is found, the /proc/k message file is used as a source of kernel log information. If the proc file system is not mounted, the kernel log daemon uses a system call to obtain kernel messages. The command line switch -s can be used to force klogd to use the system call interface as its messaging source. Last searches back through the file /var/log/wtmp, or the file designated by the -f flag, and displays a list of all users logged in and out since that file was created. Names of users and TTYs can be given, in which case last will show only those entries matching the arguments. Names of TTYs can be abbreviated, thus last 0 is the same as last TTY 0. When last catches a SIGINT signal generated by the interrupt key, usually Ctrl-C, or a SIG-quit signal generated by the quit key, usually Ctrl//, last will show how far it has searched through the file. In the case of the SIGINT signal, last will then terminate. The pseudo-user reboot logs in each time the system is rebooted. Thus, last reboot will show a log of all reboots since the log file was created. Less is a simple, feature-rich command line file viewer. It's a program similar to more, but it has many more features. It does not have to read the entire input file before starting, so with large input files it starts up faster than text editors like Vim. And Less uses a term cap, or term info on some systems, so it can run on a variety of terminals. There is even limited support for hard copy terminals. On a hard copy terminal, lines which should be printed at the top of the screen are prefixed with a caret. Commands are based on both more and VI, and commands may be preceded by a decimal number called n. And that's about it for today. Don't forget to like, share, and subscribe. Any questions you might have are to be left down in the comment section or on our website www.sosit.co. Again, that's www.sosit.co. Thanks for watching and have a nice day.